In the last lecture, we have seen random variable and then we defined cumulative distribution function, which is basically nothing but probability that x is less than equals to x. And then we have seen some of the examples of the random variable as well as their distribution functions. And finally, we talk about that we can write the probability that x belongs to different kind of intervals using the distribution function. Today we are going to see what is called discrete random variable. So discrete random variable is basically a special type of random variable, and we are going to see this discrete random variable. And this one is obviously very useful in practice, especially in computer science stream. So now note that when we talk about the distribution of different random variables, we are giving the examples. We have seen that we are basically seen some of the examples like one of the case the distribution function is given by this expression, which is nothing but if I uh, toss a coin two times, what is the random variable x is the number of tails out of two throws. So if I talk about this random variable, you see that this distribution function is a step function. That means that for x less than 0, it is 0, and between 0 to 1 it is again constant as 1 by 4, then 1 to 2 it is again constant 3 by 4, and more than 2 it is 1. Okay, so this function is basically something like steps, that you have the constant value here, then you have jump, and then there you have again constant values, again you have jump, and so on and so forth. It is going on. Similarly, in example 2.5 also we have that distribution function, the cumulative distribution function is a step function. You have jump and then constant value, again jump and constant value, and so on and so forth. On the other hand, if you see the example 2.6, and if I talk about the distribution function of x1, this function is continuous as well as smooth. It is a smooth continuous function. Okay, so we have that distribution function of a random variable can take different shapes, and based on that we divide the random variable into different categories. So two of the categories we are going to discuss in this course are discrete random variables and continuous random variables. So discrete random variables basically intuitively mean that this random variable can take some discrete values, just like this example, that example 2.4, example 2.4 or example 2.1, the random variable was the number of tails out of two tosses of a coin. And clearly in this case the x can take value either 0 or 1 or 2, so it can take discrete values. Or on the other hand, when can take only discrete values, that means we have only probability at those points. And we have pointed out this thing that if the probability of x equals to x is strictly greater than 0, then we will have a jump at the point x in the distribution function of x. So that means that when the random variable can take some discrete values, the distribution function will be a discontinuous function, and if I add up the jumps, that has to be 1. So that actually going to give us the definition of the discrete random variable. Exact definition I am coming. And another random variable we are going to talk about is continuous random variable, when the distribution function is nice, smooth, and continuous function. So mathematical definition of the continuous random variable will be little bit different, but yeah, basically intuitive idea is that it is a nice, smooth function. Okay, that cumulative distribution function is a nice, smooth function. So now let us talk about the exact definition of discrete random variable. So it says that a random variable said to have discrete distribution if there exists an at most countable set Sx, which obviously is a subset of R, such that x equals to x is strictly greater than 0 for all x belongs to Sx, and summation probability x equals to x equals to 1. If these two conditions hold true, that if I can find out a countable set, at most countable set, such that for each point in the at most countable set, the probability is strictly greater than 0, and if the sum of the probability that x belongs to Sx, which is basically that the probability that x belongs to Sx, which is basically nothing but the sum over x belongs to Sx, probability x equals to x. If this quantity is 1, that means if the probability that x belongs to Sx is 1, we call the corresponding random variable as the discrete random variable, and the corresponding distribution as the discrete distribution. This set Sx has given a name. It's called the support of the random variable x, and you see that if small x does not belongs to capital Sx in case of a discrete random variable, the probability will be 0, because the total probability inside the Sx is 1. So if I go outside Sx, it will be 0. In this case, we have another quantity, another function, which is nothing but fx equals to probability x equals to x. Now, clearly, if x belongs to the support, then it will be probability x equals to x. If it is outside the support, it will be 0. And this particular function is called probability mass function. Okay. So this probability mass function we define only for the discrete random variable. So if I have a discrete random variable x, then probability mass function defined by if fx at the point small x is nothing but probability x equals to x, and which is clearly can be written into two parts. If x belongs to Sx, it will be probability x equals to x. If x does not belongs to Sx, the probability is 0. Okay. So now let us try to understand this thing with some examples. And the first example, again, the continuation of the example 2.4, where we are talking about number of um, tails or number of heads when we throw a die 2 times. Sorry, when we toss a coin 2 times. So in this case, as we have already pointed out, the distribution function is a step function. The distribution function is a step function that basically mean that, well, that basically mean that the distribution function. So this is the example uh, 2.7, and in this case basically we have the distribution function if x at the point x is equals to 0, 1 by 4, 3 by 4, and 1. This is if x is less than 0, if 0 is less than equals to x is less than 1, if 1 is less than equals to x is less than 2, and if x is greater than equals to 2. As we have already pointed out this thing, that in this case the distribution function is 0 up to this point. Obviously here it is open, then it is basically this, and then we have another step, and finally it reaches to 1. So this value is 2, this value is 1, this value is, I'm sorry, this value is 1, this value is, I'm sorry, 0, 1 by 4, and then this, and then this. So I'm sorry, this should be of this form, that, well, this value is basically, this value is 1 by 4. I have jump of 1 by 4. Then this value is 3 by 4. I have jump of half, and then this jump is again 1 by 4. So this value is 1. Finally we reach 1. Okay. So in this case the function is a step function, and you see that if I take a set D, which is consist of the point 0, 1 and 2. So what points I have taken? I have taken the points where I have the discontinuity. And the reason is clear. The reason is nothing but, see, in the definition we have that we need to find out a countable set Sx on which the probability is strictly greater than 0. What does this mean? This basically means that if I, and we have already pointed out that a random variable has probability x equals to x is strictly greater than 0 if we have a jump, we have a discontinuity at the point small x in the function capital X. If the cumulative distribution function is discontinuous at the point small x, then we have probability x equals to x is strictly greater than 0 and vice versa. So that's why basically when we try to check if a random variable is a discrete or not, what we are going to do is that we are going to take a collection of sets which are nothing but where we have discontinuity in the cumulative distribution function. Once we start with this set, and now once we have this, I will able to find out what is the probability that x equals to 0, x equals to 1, and x equals to 2. This is simple because we know that probability x equals to small x can be written as probability x at the point small x minus probability x at the point small x minus, which basically means the left hand limit. Okay, so this quantity I can write in this form, and once I write in this form, I will be able to find out what is the probabilities from the distribution function, and and those probabilities are 1 by 4, half, and 1 by 4. So that is the amount of the jump, okay, length of the jump. So once I have that, I can find out what is the probability x belongs to D, which is nothing but sum of these probabilities, and in this case, it turns out to be 1. So what we have a finite set which is at most countable 1, and for each point in this finite set, we have the probability that x equals to small x is strictly greater than 0, and also we have probability x belongs to D is equals to 1. So that means this random variable satisfy all the property of a discrete random variable. So this x is a discrete random variable where the support is 0, the set 0, 1, and 2. Okay, so and in this case we can easily able to write what is the probability mass function PMF. What is the probability mass function? We will able to write very easily, and that is nothing but, as we got in this case, that probability x equals to 0 is 1 by 4, probability x equals to 1 is half, and probability x equals to 2 is 1 by 4. So the probability mass function, which we will write as PMF, probability mass function is nothing but, in this case, f of x at the point x is 1 by 4 if x equals to 0, half if x equals to 1, 1 by 4 if x equals to 2, and it is 0 otherwise. So note that when we defined when we define the probability mass function PMF, we define it as a function from R to 0 to 1. So clearly we have to define the probability mass function for all values of x, and that was we have done in this case, that we have written that, well, probability mass function is 1 by 4 at the point 0, half at the point x, 1 by 4 at the point 2, and it is 0 for all other values of x. Okay, so this is basically the idea of this is basically the definition and the definition of discrete random variable and probability mass function. And as I have already mentioned, that this probability mass function we define only for discrete random variable. Okay, so now you see, let us see some of the basic property of the discrete random variable. Okay, before going into the discrete other properties of the discrete random variable, two more examples. This example, example 2.8 is continuation of the example 2.5. So example 2.5 was basically nothing but we had this cumulative distribution function, and in this case also you can see that this cumulative distribution function, if you take the all discontinuity points, which is 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12, you will be able to see that in this case, if you add up the amount of jumps, the length of jumps, it will be 1. So in this case, it will turns out to be a discrete one. But if you think of the next example, which is 2.3, in this example, the distribution function is a nice continuous function, and so it does not have a jump. And if it does not have a jump, that means the probability that capital X equals to small x is equals to 0 for all small x belongs to R. And that means that this random variable cannot be a discrete random variable. Okay, clear? So that is basically, so that means basically in three examples we discussed in the last lecture, two of them are discrete random variable, whereas another one is not a discrete random variable. So those two examples are given here. So those two examples are given here, and we have that, well, that one is discrete and the other cases they are not discrete. Okay, so now note that, uh, so that what does this mean? That means that if I have a cumulative distribution function, sorry, if I have a cumulative distribution function, I can check if the random variable is a discrete random variable or not. If it is a discrete random variable, I can find out what is its PMF just writing that it is probability x equals to x, which is basically nothing but if the cumulative distribution function at the point x minus left limit of the cumulative distribution function at the point x. So that means that given a cumulative distribution function, if it is the cumulative distribution function of a discrete random variable, I will be able to find out what is the probability mass function or PMF. On the other hand, if I am given with PMF, that means that the corresponding random variable the corresponding random variable have to be a discrete random variable. So in this case, if I given with a PMF, I will able to find out what is the cumulative distribution function just taking this sum, because the cumulative distribution function is nothing but the probability that capital X is less than equals to small x, and this small fx is nothing but probability that capital X equals to small x. So if I try to find out the probability that capital X less than equals to small x, which is nothing but the probability, sum of the probabilities up to the point small x. So that was nothing but f of x, y, and you need to take the sum over y less than equals to x. Obviously, if I take the sum over only the points in the support, I am done, because probabilities are only positive for points in the support. Outside that, it is zero. Okay, so that this discussion tells us that from cumulative distribution function I will able to find out the probability mass function. On the other hand, from the probability mass function I will able to find out the cumulative distribution function, CDF. So this cumulative distribution function and probability mass function for a discrete random variable has a one-to-one correspondence, in the sense that given one, I will able to find out the other uniquely. Okay, so this is basically kind of a one-to-one relationship between these two functions, the cumulative distribution function and probability mass function, PMF, in case of the discrete random variable. Let us see some of the property of the PMF. So basic two property of the PMF, and these two coming from the definition itself. The first quantity says that, well, probability mass function has to be strictly greater than 0 for all real numbers. And it is obvious because of the definition we write that probability mass function is nothing but the probability x equals to capital X equals to small x. So clearly that probability has to be greater than equals to 0. So that's why that this quantity has to be greater than equals to 0. Obviously, as it is a probability, it has to be less than equals to 1 also. And then if I take the sum of the probability over the support, it has to be 1. This is also straightforward because this sum is nothing but probability x belongs to the support, probability that capital S, the random variable, belongs to the support, and that for the discrete random variable, by definition, that probability capital X belongs to the support is equals to 1. So these two properties are straightforward consequence of the definition of discrete random variable as well as probability mass function. The interesting thing is that which the proof cannot be given here is basically theorem 2.4. What it says? It says intuitively that if some random variable, if some function satisfies both the conditions here, it will turns out to be a probability mass function. So that means that if I have a function h from R to R, which satisfy these two conditions, the first condition says that hs is strictly greater than equals to 0 for all real numbers. So that is basically corresponding to this one. And if the hs is strictly greater than 0, hs is strictly greater than 0 only on a finite set or countable infinite set. And this set is said to be D. So this D actually plays the role of the support here. And in this case, if I take the sum of this h function over the D, if this sum turns out to be 1, then this h function will be the probability mass function PMF of some discrete random variable. Okay, so if a function satisfies two conditions, one of them is x, the function is greater than equals to 0 for all real numbers, and the function is strictly greater than 0 only on some at most countable set, and if I take the sum of the function over that countable set, it turns out to be 1, then that function h is a probability mass function of some discrete random variable. Proof cannot be given here, but this theorem is very helpful because with given a function, we can check if the function is a probability mass function or not. Just recall that we have some conditions to check if a given function is a cumulative distribution function or not. Basically, we need to check 4 conditions there. Similarly, given a function, I can check that whether that function is a probability mass function or not by checking the points 1 and 2, by checking the conditions 1 and 2. Okay, now let us stop here. In the next lecture, we will see some of the example of the discrete random variables which are used in practice, which are hugely used in practice.